record button. Okay, I'm now recording. Okay, so exam major and minors. Exam 2 is on December 2nd in class on Zoom. Exam 3 is on December 9th in class on Zoom. The class before each exam, I'll give you a review. We'll need to extend class time to fit that in. Final is going to be during finals week. Okay, so I made another extra video on YouTube. And so that video will cover all the remaining homeworks for test 2 and the material for test 2. And so we review on November 30th, and the second exam will be on December 2nd. Okay, let's start the material. 4.4 is on coordinates and bases, Okay, I typed this up ahead of time. Definition 1. If S is a set of vectors in a finite dimensional vector space V, then S is called the basis for V. If A, S spans V, B, S is linearly independent. You can talk to me now about exam 3 if you want. Okay. But I do need to cover the material. So maybe we can talk later. That's probably better. Okay. So definition 1, if S is that set is a set of vectors in a finite dimensional vector space V, then S is called the basis for V if A, S spans V, B, S is linearly independent. Think back to describing a coordinate system for a finite dimensional vector space V. Okay, you're welcome. So A guarantees that there are enough basis vectors to provide coordinates for all vectors in V, and B guarantees there's no interrelationship between the basis vectors. Okay, so that set of vectors is a basis if it spans your vector space and it's linearly independent. The meaning of a set spanning a vector space, in a sense, is that the vectors themselves can form coordinate axes for your vector space, okay? And saying your set is linearly independent is saying that among the vectors in the set, there's no interrelationship between those vectors. You can't think of any one of those vectors as a linear combination of the other one, okay? It's the most efficient, having a basis is the most efficient way of having coordinate axes for your entire vector space, okay? In R3, you would have 3 coordinate axes, right? And so your basis should have 3 vectors, okay? You can't make a basis. You can't make coordinate axes with just 2 axes. You can't make coordinate axes for R3 with two axes. You need 3, right? And so if you only had 2 vectors, you couldn't span the space. If you had 4, you could span it with 4 coordinate axes, but the set would be linearly independent. Would be linearly dependent. You can in a sense take 2 of your axes and just reduce it to 1. Example 1, the standard unit vectors E1 to En span Rn and are linearly independent. Thus, they form a basis for Rn. Okay, so the standard unit vectors E1 to En span Rn. Okay, any vector in n space can be thought as a linear combination of the vectors E1 to En. So those vectors span Rn, and those vectors are linearly independent. So if you have a set of vectors that span a vector space and they are linearly independent, they form a basis for Rn. That's by this definition in definition 1, the definition for a basis. In example 2, this set forms a basis for Pn, a polynomials of degree at most n, since the set spans it and is linearly independent. Okay, so that set is linearly independent and it spans Pn because every polynomial can be thought as a linear combination of the vectors in that set. Okay, so that set spans Pn and all those vectors are independent. Okay, so V1, V2, and V3 form a basis for R3. So those 3 vectors form a basis for R3 because they are linearly independent and they span R3. Okay, so any vector in R3 can be thought of as a linear combination of V1, V2, and V3, and they are linearly independent. Okay. Okay, so to show that they form a linearly independent set, we show that C1 V1 plus C2 V2 plus C3 V3 equals 0 has only the trivial solution. Okay, so the only way to make this equation hold is if all the vectors are 0. To show they span R3, we show every B in R3 can be expressed as B is equal to that linear combination. Okay, so we want to express every vector B in R3 as a linear combination. Correspondingly, we need to show that that this system has only the trivial solution, and that this linear system is consistent for all values b1, b2, and b3. Okay, so if you have a vector b, right? Okay, so you just replace the vectors v1, v2, and v3 here by these vectors, right? And so you have components, you have the first, second, and third components here when you do the arithmetic, and you have the first, second, and third components of b there. Okay. For this equation, you have first, second, and third components for that, and you have zeros there. And so the first component is both 0, the second component is both 0, and the third component is both 0. For this one, where b is equal to this, you have a first, second, third components here, and you have the first, second, and third components of b there. And so correspondingly, you want the first component to equal the first component, second component to equal the second, and the third component to equal the third. And you want to show this is consistent for all values b1, b2, and b3. Because to show that there are c1, c2, and c3s where this equation holds is equivalent to saying that this linear system has at least one solution for all the b1, b2, and b3s you could put there. Okay, so in order to show these two statements, or to show that this has only a trivial solution, and this is consistent for all values b1, b2, and b3, they can both be proven at the same time by showing that the coefficient matrix A of this linear system has determinant non-zero. Okay, if you show the determinant of the coefficient matrix is non-zero by theorem 2.3.8, or the equivalence theorem, parts B, E, and G, it means that AX equals 0 has only the trivial solution, and AX equals B is consistent for every n by 1 matrix B. Okay, so by knowing the determinant is non-zero, that's equivalent to saying that AX equals 0 has only the trivial solution. It's also equivalent to saying AX equals B is consistent for every n by 1 matrix B. Okay. Okay, so when you find the determinant of that matrix A, you get equals -1. And that proves then that V1, V2, V3 forms a basis for R3, because it shows that this system has only the trivial solution, which means that the only values you can plug in for C1, C2, and C3 there are 0. So this only has the trivial solution, which means that V1, V2, V3 is a linearly independent set. Also, from the determinant being non-zero, you know that AX equals B is consistent, has at least one solution for every n by 1 matrix B. Correspondingly, that means this system has at least one solution for all B1, B2, B3s, which means that every B in R3 can be expressed in that way. Okay, and so that shows it spans R3. So we have a linearly independent set that spans R3, and so these three vectors form a basis of R3. Okay, so in example 4, we have these 4 matrices, and they form a basis for M sub 2, 2, which is the vector space of 2 by 2 matrices under the operations of normal matrix addition and normal scalar multiplication of matrices. Okay, so this forms a basis. Okay, so every vector, every matrix, every vector in M sub 2, 2 is a 2 by 2 matrix, right? So every 2 by 2 matrix or vector in M sub 2, 2, it can be written as a linear combination of those 4 matrices. And so these 4 matrices span M sub 2, 2. These 4 matrices as vectors are also linearly independent, form a linearly independent set, because no one of those matrices can be expressed as a linear combination of the other 3. Okay, and so I wrote that here. So this has only the trivial solution, and this is consistent for every 2 by 2 matrix B. Okay, and so good. Okay, so then these 4 matrices form a basis for M sub 2, 2. More generally, the set of m by n matrices whose entries are 0, except for a single entry of 1, form a basis for M sub m cross n. Sure. Okay. So you're welcome. Okay, so these four matrices form basis for M sub 2, 2. Okay, if anyone has questions, just ask. More generally, the set of M by N matrices whose entries are 0 except for a single entry of 1 form a basis for M sub M cross N, called the standard basis for M sub Mn. Okay, so it forms a standard basis for M, capital M sub Mn. Okay, so so note the null set is a basis for the 0 vector space. Okay, so the basis for the 0 vector space is the null set. Okay, example 5. The vector space P infinity of all polynomials with real coefficients is infinite dimensional since it has no finite spanning set. Okay, there is no finite spanning set for P infinity. Okay, no matter what, if it did, all polynomials would have a maximum order. Okay, if you had a finite spanning set, then there would be some element of that finite spanning set with largest order, right? So let's say it was order n. So if you had finitely many polynomials that you thought would span P infinity, then one of those polynomials would have a maximum order, say n. And so if you just took a polynomial with an xn plus 1 term, there'd be no way to express that as a linear combination of the polynomials in your spanning set. Your polynomials would have some maximum order, and then a polynomial of order greater than that could not be expressed as a linear combination of the vectors in that spanning set. Okay, and so that contradiction means that there is no finite spanning set of P infinity. And so P infinity is an infinite dimensional vector space. Okay, when a vector space has no finite spanning set, it is infinite dimensional. Okay, examples of finite dimensional spaces. Rn is finite dimensional because it's n dimensional. Pn is finite dimensional because it's n plus 1 dimensional. M sub Mn is finite dimensional because its dimension is m times n. So those three are finite dimensional vector spaces. Okay, infinite dimensional spaces. P infinity we proved was an infinite dimensional vector space. R infinity is also an infinite dimensional vector space. It's the space of all infinite tuples. It's the space of all of ordered infinite tuples. Lists, infinite lists. It's the space of all infinite lists, countable infinite lists. Capital F of negative infinity, comma infinity is the space of all continuous functions on the real line. This is also an infinite dimensional space. It cannot be spanned by a finite spanning set. Capital C of negative infinity, comma infinity is the space of all continuous functions on the real line. This is the space of all functions on the real line. This is the space of all continuous functions on the real line. This is the space of all functions that are continuously differentiable up to and including order m. What that means is the functions whose derivatives exist and are continuous up to and including order m. So the 0th derivative is continuous and exists. The first derivative is continuous and exists, ... The mth derivative is continuous and exists. C infinity is the space of all functions that have continuous derivatives that exist of all orders that are defined on the real line. That space is also infinite dimensional. So those 6 are examples of infinite dimensional vector spaces. Those 3 are examples of finite dimensional vector spaces. Okay, next theorem is theorem 4.1.1. If S is that set is a basis for a vector space V, then every vector little v and capital V can be expressed in the form V is equal to that linear combination in exactly one way. So if you have a basis for a vector space, then every vector can be expressed in exactly one way as a linear combination of those basis vectors. Okay, so given a basis for a vector space, every vector can be expressed in exactly one way as a linear combination of those vectors in the basis. That's the theorem. Okay, so the power of that statement is one of the reasons why basis is so important. Okay, having a basis for a vector space means you can have, there's exactly one way to express every vector as a linear combination of those vectors in the basis. Okay, bases are not unique, but for each basis, there's exactly one unique way to express every vector as a linear combination of those basis vectors. Okay. Definition 2. If S is again a basis for a vector space V, and you have a little v in that space, which is that linear combination, and say that is the expression for a vector little v in terms of the basis capital S, then the scalars C1 to Cn are called the coordinates of V relative to the basis S. The vector C1, C2 to Cn in Rn is called the coordinate vector of V relative to S. Okay, so if you have V, which is expressed in this way, you can just think of the coefficients of the basis vectors in that order as being the components of the coordinate vector of V relative to S. Okay, so the coordinate vector of V relative to S is equal to this ordered n-tuple C1 to Cn, where those are the coefficients of the linear combination that expresses that vector V. Okay, we know that from the previous theorem that given a fixed basis, there's exactly one way to express a vector as a linear combination of those vectors in the basis. And so there's exactly one assignment of coefficients for those vectors. So there's exactly one n-tuple that we define in this way, given a fixed basis S. And there's a one-to-one correspondence between points little v and capital V and the coordinates relative to the basis S in Rn. Okay, so every vector V in your vector space, of course, there's a corresponding coordinates of it relative to a fixed basis S in Rn. And for any n-tuple in Rn, you can think of that n-tuple as being coordinates of a unique, distinct vector in your vector space. Okay, so given coordinates relative to a basis S, there's some vector in your vector space whose coordinates are those coordinates. Example 7. In the special case V is equal to Rn and S is the standard basis, the vector V is equal to its coordinates relative to the standard basis. So if you have a vector space V, which is Rn, and S is the standard basis, if you take the coordinates of a vector relative to the standard basis, its coordinates are the same as the vector itself. For example, if you have a vector V, which is ABC, then the coordinates of V relative to S is equal to ABC. Since that vector V can be expressed as equal to AI plus BJ plus CK. I, J, and K are the standard unit vectors for R3. And so V is equal to AI plus BJ plus CK. And so the coordinates of V relative to S is A comma B comma C. But that's already V. So V is equal to its coordinates relative to that basis S. And so that shows how that happens in R3. In general, for Rn, you can do a very similar proof for any dimension. In example 9, part A, we have find the coordinate vector of this vector V relative to this basis in example 3. So we have these three vectors, V1, V2, and V3. And we want to find the coordinates of this vector V relative to the basis containing those three vectors. Equivalently, we want to take this vector V, 5, negative 1, 9, and write it as a linear combination of vectors V1, V2, and V3. And that means we need coefficients C1, C2, and C3 for that linear combination. And so we have this equation, right? If we can find values, assignments of C1, C2, and C3 that make this equation hold, then we have found a way to write this vector as a linear combination of those three vectors. And that C1, C2, C3 correspondingly form the coordinates of your vector relative to that basis. So you have this equation. Equivalently, you have a linear system, right? Where the first equation is saying the first component on the left side is equal to the first component on the right side. The second equation is that the second component equals the second component. And the third equation is that the third component equals the third component. So you have these three equations corresponding to this one equation. And so the goal is to find all solutions, C1, C2, and C3 of that linear system. So you can solve the system using Gauss-Jordan elimination, and you get that C1 equals 1, C2 equals negative 1, and C3 equals 2. Therefore, we've now found coordinates of our vector V relative to this basis S, and it's 1, negative 1, 2. So the coordinates of V relative to this basis S with those three vectors is 1, -1, 2. Those are the coefficients of those vectors written as linear combination to equal the vector V. So part B is find the vector V in R3 such that its coordinates relative to S is equal to -1, 3, 2. So we want V to equal a linear combination of V1, V2, and V3 where the coefficients are -1, 3, and 2 respectively. And so you just write V is equal to that linear combination. Plug in V1, V2, and V3 given to you. You get this expression. And so then you compute that, and that's V. So V is equal to this. Okay? Oh, so V is equal to this. And then you compute that, and you get 11, 31, 7. So the vector V, whose coordinates are those, is the vector 11, 31, 7. Okay? And so we talked about what a basis is. We talked about how to find the coordinates of a vector relative to a basis. And so in this example, we found the coordinates of a vector relative to a basis. And in B, we found a vector with given coordinates. So that's 4.4. 4.5 is on dimension. So theorem 4.5.1 says all bases for a finite dimensional vector space have the same number of vectors. So if you have different bases for the same finite dimensional vector space, they all have the same number of vectors. Bases are not distinct. You could have more than one basis. But even when you have more than one basis, they will always have the same number of vectors in them. Theorem 4.5.2 says, let V be an n-dimensional vector space. Let V1 to Vn be any basis. A, if a set in V has more than n vectors, then it is linearly dependent. So if you have an n-dimensional vector space and you have a basis for it, meaning you have to have n vectors in that basis, if you have a set with more than n vectors, that set must be linearly dependent. B, if a set in V has fewer than n vectors, then it does not span V. Okay, so if you set with fewer than n vectors, it does not span V, given that V is an n-dimensional vector space. Definition 1. The dimension of a finite dimensional vector space V is denoted by dim V and is defined to be the number of vectors in a basis for V. Okay, so when you have a fixed vector space, you can have different bases for it, but all of those bases always have the same number of vectors. For a finite dimensional vector space, that number that's the same for all of those bases is the dimension of that finite dimensional vector space. Okay, the zero vector space has dimension 0 by definition. Example 1, the dimension of Rn is n because any basis for Rn has exactly n vectors. So the dimension of it is n. The dimension of P sub n is equal to n plus 1 because any basis for P sub n has n plus 1 vectors in it. The dimension of M sub Mn is m times n because any basis for M sub n Mn has exactly m times n vectors in it. Example 2. If S is the set V1 to Vr is a linearly independent set, then the dimension of the span of S is equal to R. So if you have a linearly independent set with R vectors in it, the dimension of its span is equal to R. Okay? The span of a set, again, is the set of all linear combinations of those vectors. And so if you have R vectors that form a linearly independent set, and you consider the set of all linear combinations of those R vectors, the dimension of that set, big set, is R, the number of vectors in the original set. Example 3. If you have this linear system, the solution space is x1 is equal to -3r minus 4s minus 2t, x2 is equal to r, x3 is equal to -2s, x4 is equal to s, x5 equals t, x6 equals 0. Now, if you write that 6-tuple out, you can write it as a linear combination of these three vectors, r times this vector plus s times this one plus t times that one. Okay, but so now if you think the space of all solutions, you're thinking of the space of all linear combinations of those three vectors. So the space of all solutions, the set of all solutions, that linear system, is the set of all linear combinations of those three vectors with coefficients r, s, and t, respectively. So you know that these three vectors, v1, v2, and v3, these vectors here, span your solution space. They span. Every solution to that linear system can be expressed as a linear combination of those three vectors. And so those three vectors span your solution space. They are also linearly independent because this third vector has a 1 in the second to last component, and the other two will have zeros there. You cannot express the third vector as a linear combination of the first two. The second vector here has a 1 in the third to last position, and you see the other two have zeros there. You cannot express this vector as a linear combination of those other two. And this first vector has a 1 in the second component, and the other two vectors have zeros in the second component. And so this first vector cannot be expressed as a linear combination of the other two. So these three vectors form a linearly independent set, and they span the solution space. And so the set containing those three vectors forms a basis for the solution space of that linear system. It's a spanning set that's linearly independent. And so since we showed the solution space of that linear system has a basis with three vectors in it, that means the dimension of the solution space is 3. Okay. Next is the theorem 4.5.3. It's the plus minus theorem. Let S be a non-empty set of vectors in a vector space V. A, if S is a linearly independent set, and if V is a vector in capital V that is outside of the span of S, then S union that the set containing V is still linearly independent. Meaning, if you have a linearly independent set, and you have a vector V that's not in the span of that set, then if you include it in the set, you still have a linearly independent set. Okay? Okay, and part B says if V is a vector in S, if you have a linearly independent set, and V is a vector in that set, and it's expressible as a linear combination. Oh, sorry. In part B, S is a non-empty set of vectors. Okay, S is just a non-empty set of vectors again. And in B, V is a vector in that set S that is expressible as a linear combination of the other vectors in S. So this set S is not linearly independent in part B. So you have a vector V in S that is expressible as a linear combination of the other vectors in S. Okay, and so S minus the set containing V is the set that you get when you remove the vector V from the set S. Then what happens is that S and S minus V span the same set, or the span of S is equal to the span of S minus V. Okay, so if you have a vector V in your set S that is expressible as a linear combination of the other vectors in the set, then removing it does not change the span of the set. Okay, that's part B of the plus minus theorem. In example 4, we have that P1 is equal to 1 minus x squared, P2 is equal to 2 minus x squared, and P3 is equal to x cubed. Those three are linearly independent vectors. Since S is equal to the set P1, P2 is linearly independent as a set of two vectors, because neither of them are scalar multiples of the other. If you think of P1 here and P2 here, neither of them are scalar multiples of the other. And when you have a set with two vectors where neither is a scalar multiple of the other, that two-element set is linearly independent. So the set P1, P2 is linearly independent for that reason. Now the vector P3 cannot be expressed as a linear combination of the vectors P1 and P2, because P3 is x cubed, and P1 and P2, neither of them have an x cubed term. So you cannot express P3 as a linear combination of P1 and P2. And so the span of P1, P2 does not include x3. P3 is outside the span of P1 and P2. So by part A of the plus minus theorem, since you have a linearly independent set S, P1, P2, and P3 is outside of the span of that set, then including P3 in the set results in a still linearly independent set. And so S union the set containing P3, or the set P1, P2, P3, is also linearly independent. And so what I showed there in example 4 is that the set P1, P2, P3 is a linearly independent set by using part A of the plus minus theorem, theorem 4.5.3. Okay, I started with the 2-element set being linearly independent and used the plus minus theorem to show that adding the third element results in a still linearly independent set by part A of that theorem. Okay, the next theorem is theorem 4.5.4. Let V be an n-dimensional vector space, and let S be a set in V with exactly n vectors. Then S is a basis for V if and only if S spans V or S is linearly independent. Normally, to have a basis for a vector space, you need that it both spans your vector space and is linearly independent. But if you have an n-dimensional vector space, and S is a set with exactly n vectors in it, meaning the same number of vectors as the dimension of your vector space, then you only need that set to satisfy one of the two qualifications for a basis. You either need to show that it spans V or that it's linearly independent. Either one implies that you have a basis. If either one is false, that implies that it's not a basis. Okay, this is only for the special case where your set S has the same number of vectors as the dimension of the vector space that you want to know whether or not there's a basis for. Okay, and so that shortens the proof of showing a set as a basis for a vector space if you know its number of vectors is the same as the dimension of this vector space. In example 5, you have V1 and V2, and they form a basis for R2, right? When you have a 2-element set, again, since V1 and V2, neither is a scalar multiple of the other, then together they form a linearly independent set, right? So S equals V1, V2 is a linearly independent set of vectors in R2. Since it's a set containing 2 vectors, and the vector space R2 is 2-dimensional, then by our last theorem, theorem 4.5.4, this set S is a basis for R2. Okay, we know it's a basis just by knowing it's linearly independent because the number of vectors is the same as the dimension, the number of dimension of vector space. Okay, the next theorem is theorem 4.5.5. Let S be a finite set of vectors in a finite dimensional vector space. So at part A, if S spans V, but is not a basis for V, then S can be reduced to a basis for V by removing appropriate vectors from S. Okay, so once you have a set spans a vector space, the only way it would not be a basis if it's not linearly independent. Okay, because a basis means it's both linearly independent and spans. And so if it does span, but it's not basis, it means it's not linearly independent. But by this theorem, when working with a finite dimensional vector space V, you can reduce the size of your set S, in this case, to a basis by removing appropriate vectors from S. Okay, so you have a set S that's too big, it spans your vector space, but it's not a basis. And so by this theorem, you can one by one remove the vectors from S appropriately. You can't remove the wrong ones. There's a way to keep removing the correct vectors one at a time until eventually you will have a basis for your vector space from that set, only from the vectors in the set, that set S. Part B is if S is a linearly independent set that is not already a basis for V, what's happening is you have a linearly independent set, but it's not big enough. You need more vectors in it. Okay, so if you have a linearly independent set that's not a basis, that means you need more vectors in it to become a basis. It doesn't span your vector space. You need more vectors in order for the set to span it. By part B, the conclusion is that you can enlarge the set S to a basis for V by inserting appropriate vectors into that set S. So there's a way to take that too small of set that's linearly independent and add appropriate vectors to it so that you get a basis. That's theorem 4.5.5. Okay, now in theorem 4.5.6 says, if W is a subspace of a finite dimensional vector space V, then part A says W is finite dimensional. So if you start with a finite dimensional vector space V, then any subspace W of V is also finite dimensional. The part B says that the dimension of this subspace W is less or equal to the dimension of V. And C says W equals V if only if the dimension of W equals the dimension of V. Okay, so that's that theorem. Okay, now 4.6 is about change of basis. So if S is this set, is a basis for a finite dimensional vector space V, and if the coordinates of a vector V relative to S is equal to C1 to Cn, then the mapping that maps a vector V to its coordinates relative to fixed basis S creates a one-to-one correspondence between the vectors in V and the vectors in Rn. Okay, I'm going to go to the whiteboard and illustrate that. So, if you have a vector space V, and you have any vector V in it, then the map that sends V to its coordinates relative to a basis S, this will there'll be a one-to-one correspondence between a vector and its components relative to a fixed basis S. Okay, so you have your vector space V, and you have your Rn space here. Okay, the dimension is n. So there's a one-to-one correspondence between the vectors in your vector space and n tuples in Rn, or their coordinates relative to a fixed basis S. Okay, so for any vector in V, there's a one-to-one correspondence between and with its coordinates relative to fixed basis S. Okay, so this map in 1 is the coordinate map relative to S from V to Rn. It's the coordinate map relative to S from V to Rn. We will denote coordinate vectors in the matrix form, in this form. Okay, so the coordinates of vector V relative to a fixed basis S is equal to this. And so instead of expressing it as an n tuple horizontally, you can express it as a matrix vertically. Okay, it's still a list of n things in the same order. It's just a vertical list instead of a horizontal. Okay, and the next thing is about the solution of the change of basis problem. Okay, if we change the basis for vector space B from an old basis B prime to a new basis B, then for each vector V, the old coordinate vector is related to the new coordinate vector by this equation. Okay, this is the coordinates of your same vector with respect to an old basis. These are the coordinates of that vector V relative to a new basis. The vector stays the same, but you're expressing them relative to new and old coordinates. The relation includes this P here, and it's a matrix where the columns of P are the coordinate vectors of the old basis vectors relative to the new basis. That is, the columns of P are these vectors. So the first column of P is the coordinates of the first old basis vector relative to the new basis. The second column is the coordinates of the second old basis vector relative to the new basis. The third column is the coordinates of the third old basis vector relative to the new basis. So the primes, the U primes, are the old basis vectors. The U's without primes are the new basis vectors. Okay, the old basis is B prime and the new basis is B. So the goal is to find this transition matrix P. Okay, this transition matrix P is built by columns. So you want to find the columns of P one at a time. Okay, you want to find the first column of P, then the second, then the third, dot, 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 then the nth. Okay, to find the first column of the transition matrix P, you want to take the first old basis vector, U1 prime, and express it as a linear combination of the new basis vectors. Okay, so there's exactly one way to do that. There's exactly one way to take the first old basis vector, U1 prime, and express it as a linear combination of the new basis vectors, U1 to UN. The coefficients of that linear combination correspond with the components of the vertical matrix U1 prime sub B. Okay, those are the coordinates of the old basis vector U1 prime relative to the new basis B, consisting of the new basis vectors U1 to UN. So these matrices are columns, or column vectors that make up the columns of the transition matrix P. This is the transition matrix from an old basis B prime to a new basis B. Okay, and so for this transition matrix, in that direction from old B prime to new B, the columns of this matrix P, again, are these column matrices, where again, they are the coordinates of each old basis vector relative to this new basis. It's taking each old basis vector and writing them each as a linear combination of all the new basis vectors. The coefficients of that linear combination correspond with the components of the column of these columns that make up the transition matrix P. Okay, so again, the first column is the coefficients of the linear combination of U1 to UN that equals U1 prime. If you take the second old basis vector and write it as a linear combination of the new basis vectors, the coefficients of that linear combination are the components of this matrix. You do that n times, and those are the columns of this transition matrix P from the old basis B prime to the new basis B. The matrix P in equation 7 is called a transition matrix from B prime to B. It will be denoted oftentimes by P sub B prime arrow B. This P means transition matrix. This B prime means, in a sense, the old basis. Arrow means going to, and to new basis B. So the fact is B prime arrow B is saying you're thinking of B prime as the old thing, and you now have a new thing B. You're going from old to new, right? So B prime to B. It's transition matrix from B prime to B. B prime arrow B down there. If you want a transition matrix from B to B prime, the notation would have B arrow B prime in the down there. Okay, so this thing here, this implies that the transition matrix from B prime to B is equal to this matrix, where I'm writing, instead of saying these are the columns, I'm putting them as columns. So this is the matrix whose first column is that matrix. The second column is this one, dot, dot, dot. The last column is that matrix. They're vertical matrices, the column matrices. And also, if you have the transition matrix in the opposite direction from B to B prime, you're going to express each new basis vector, each of the. So I was using old and new, right? Old was B prime, new was B. Technically, because we reverse the order, technically the old basis is now B and the new one is B prime because we're going in the opposite direction, okay? And so since the old basis is now B, you're taking the first basis vector in your now old basis B and expressing it as a linear combination of the now new basis vector B prime. And that's the first column of the transition matrix from B to B prime. Okay, so whichever the order of the arrows is, the one here is the old one, and the one here is the new one. And the goal to get the transition matrix is to take each basis vector in your old basis and write it as a linear combination of the vectors in the new basis. The coefficients correspond with the components of the column vector in the appropriate column of your transition matrix. The columns of the transition matrix from an old basis to a new basis are the coordinate vectors of the old basis relative to the new basis. So that's what I was saying. I was saying the columns of the transition matrix are coordinate vectors of each old basis vector relative to the new basis. Example 1. Consider the bases B and B prime for R2, where B is U1, U2, B prime is U1 prime, U2 prime. So see how without prime and prime corresponds with the name of it. U1 is 1, 0. This vector is 1, 0. And U2 is 0, 1. U1 prime is 1, 1. And U2 prime is 2, 1. So I want to find the transition matrix from the old basis B prime to new basis B. So to do that, we want the first column of this transition matrix to be the first. We want to take we want to take the first old basis vector, which is, so U1 prime, see, it's a transition matrix from B prime to B. So here, B prime is the old basis, B is the new basis. B prime is the old basis. The basis vectors in the old basis are U1 prime and U2 prime. So for your transition to get the columns of your transition matrix, you want to take each old basis vector, u1 prime and u2 prime, and express them as linear combinations of the new basis vectors, which are u1 and u2. Do you want the first old basis vector, you write as a linear combination of u1 and u2, the new basis vectors. The second old basis vector, you write as a linear combination of the new basis vectors. The coefficients of those linear combinations correspond with the columns of the transition matrix. So the first old basis vector is 1 times the first new basis vector plus 1 times the second new basis vector. And so in the first column, you have 1, 1, which corresponds with the 1, 1 here. This one corresponds with this. And this one corresponds with that. The second old basis vector, you write as this linear combination. And so this 2 corresponds with that 2. And this one corresponds with that one. And so now the first old basis vector written as a linear combination of the 2 new basis vectors gives you the first column. And the second old basis vector written as a linear combination of the new basis vectors gives you the components of the second column. And so that's the transition matrix from the old basis B prime to new basis B. And so in part A, we found the transition matrix from B prime to B. In part B, we want to find the transition matrix P from B to B prime. And so now the order is reversed in the arrows. And so now B is the old basis and B prime is the new basis. Okay, so the first old basis vector is U1 in part B. And so you want to express U1, the first old basis vector, as a linear combination of the new basis vectors U1 prime and U2 prime. And so the unique way to do that is U1 is equal to -1 U1 prime plus 1 U2 prime. The coefficients of that linear combination in the appropriate order give you the components of the first column of the transition matrix from B to B prime. And so those 2 numbers give you correspondingly the first column of that transition matrix. The second old basis vector U2 is equal to this linear combination of the 2 new basis vectors U1 prime and U2 prime. The coefficients of that linear combination correspondingly give you the components of the second column of your transition matrix. And so now that's the second column of your transition matrix. So we've now found the transition matrix from B to B prime. So for every vector V in capital V, we have that the components of that vector V relative to basis B is equal to the coordinates of that vector relative to a basis B prime, left multiplied by the transition matrix from B prime to B. And we have the coordinates of that vector V relative to a basis B prime is equal to its coordinates relative to a basis B left multiplied by the transition matrix from B to B prime. In a sense, you can think of this as taking the coordinates of vector V relative to a basis B prime and then changing it to its coordinates relative to B, see B prime to B. And here, you can think of it as changing the coordinates of a vector relative to a basis B, changing it to coordinates of a basis of changing its coordinates to coordinates relative to a basis B prime. And you can think of this as being transitioning from B to B prime, going from coordinates relative to B to coordinates relative to B prime. Okay, and so equations 11 and 12 provide a way of, if you know the coordinates of V relative to one basis, you can find its coordinates relative to another basis if you know the transition matrix from one basis to the other. Okay, this is example 2. Let B and B prime be bases in example 1. Find the coordinates of V relative to B, given that the coordinates of V relative to B prime is equal to -3, 5. So we just have its coordinates relative to B prime. And so we're going to use the equation 11 to find its coordinates relative to B by left multiplying it by the transition matrix from B prime to B. And so the transition matrix from B prime to B we found in part A, which is this matrix here, 1, 2, 1, 1. So you just take that matrix 1, 2, 1, 1, and let the multiply your coordinates of your vector B relative to B prime by that matrix. And by equation 11, it tells you that the resulting product of these matrices, 7, 2, is the coordinates of V relative to the basis B. Okay? So knowing the transition matrix from one basis to the other allows you to convert coordinates of a vector in one basis to coordinates of the same vector in another basis. So B and B prime are bases for a finite dimensional vector space V. Then the transition matrix from B prime to B times the transition matrix from B to B prime is equal to the transition matrix from B to B, which is the identity matrix. Okay, so these two transition matrices are inverses of each other. If you take any one transition matrix and multiply it by the other, you get the identity. That means that these two matrices are each inverses of each other. So theorem 4.6.1 says if P is the transition matrix from a basis B prime to a basis B for a finite dimensional vector space V, then P is invertible and P inverse is a transition matrix from B to B prime. That's what 13 is saying. It's saying that if you have a transition matrix from one basis to the other, either this one or this one, its inverse is the transition matrix of the bases going in the opposite direction. So that's theorem 4.6.1. Okay, so here is a procedure for computing the transition matrix from B to B prime. Step one is form the matrix B prime partitioned by B. Step two is use elementary row operations to reduce the matrix in step one to reduce row echelon form. Step three is the resulting matrix will be this matrix. And step four is extract the matrix, the transition matrix from B to B prime, from the right side of the matrix in step three. So you start with this matrix. On the left side, you have a partition matrix with two parts. On the left is your B prime, and on the right is your B. Okay? So B prime and B are each bases with vectors. Okay? And so that means that the columns of this side are formed by the vectors in basis B prime. Okay? So note that the columns of B prime B are the vectors in B prime B. So for each of them. So that means that B prime as a matrix is a matrix whose columns are built from the vectors of B prime. And the matrix B is the matrix built from the columns of the vectors in B. Okay. So you form that matrix. The left side is the columns of the basis B prime, and the right side are the columns of the basis B. They use elementary row operations to get this matrix in reduced row echelon form. The resulting matrix would be the left side is the identity matrix, and on the right side is the transition matrix from B to B prime. And then you just extract the matrix on the right side of the partition, and you get the transition matrix from B to B prime. Okay, keep in mind that it's the transition matrix from B to B prime because on the right side was B and on the left side was B prime. If you switch the order, if you put B on the left and B prime on the right, when you get to this step, you'll get the transition matrix from B prime to B. If you reverse the order here, you reverse the order here. Okay, so these are the 4 steps for computing the transition matrix from B to B prime. If you follow these 4 steps in this order exactly and do it correctly, you will get the transition matrix from B prime. Okay, so you have here the matrix here that I wrote here, where this is the new basis and this is the old basis, right? The columns of this matrix are from the new basis, or the new basis vectors, and the columns from this matrix are the old basis vectors, right? Remember, see, here's B and here's B prime. You get the transition matrix from B to B prime. So this is your old basis, and this is your new one, old, new. And by elementary row operations, you're getting the left side I and the right side is transition from old to new. That's just this. Okay. I'm saying step 3 again in 14. So example 3 is consider the basis B and basis B prime for R2, such that U1 is this vector, U2 is this one, U1 prime is that one, and U2 prime is that one again. We want to find the transition matrix from B prime to B using 14. Okay, so first you have your partition where the new basis is on the left and the old basis is on the right. So since the new basis is B, then you want the columns of the left side to be from B. B is the U1 and U2. So the first column is 1, 0 for U1, and the second column is 0, 1 for U2. So the new basis again, because we're finding transition matrix from B prime to B, in this example, the new basis is are the basis vectors in B. And so the columns of the left side are the vectors in B. So you have 1, 0, first column, 0, 1, the second column. Okay. And so you have this is, let's say that, and that's here. And then you have this is red, and this is the second column here. Okay, so we built the left side from your new basis vectors, right? And so these are new basis because the B is on the right side. That's the new one. I mean, wait, let me put a green here. So that's your new basis. So your new basis is because the B is on the right side here. It's a transition matrix from B prime to B. That means the result is the new one. The thing you get at the end is the new one. And your old one, I'm going to put that as brown. So it's the old one, or whatever that color is, and then that's going to be an old basis. So your old basis is the one here, and the new basis is the one here, and the vectors in your new basis form the columns of the left side, and the vectors in your old basis, which are U prime, U1 prime, U2 prime, will form the columns on the right side. But you see the left side is already the identity matrix, and so we already have the left side is the identity, which means the right side is the transition from the old to new basis. So without doing anything, we actually already have the transition matrix from B prime to B. It's this. Okay, so it's a very quick way in this example to get it, but it illustrates the procedure. The only thing it leaves out is an example where you have to do elementary row operations to get this matrix to that one. But we've done elementary row operations before. So the new thing is recognizing you have a transition matrix when that happens, which this example does singularly. Okay, so this is theorem 4.6.2. Let B prime equal to this set be any basis for the vector space Rn. And let S equal to this set be the standard basis for Rn. If the vectors are written in column form, then the transition matrix from B prime to S is equal to this matrix, where the columns are the vectors in B prime. Okay, so in this special case, in this special example, we have a basis, and then we have a standard basis for Rn. The new basis is the standard basis for Rn. And so when you express these vectors, each of these vectors, their coordinates relative to the standard basis are the same as the vectors themselves. And so in this special case, when you write the coordinates of each of these old basis vectors in terms of this new basis, which is the standard basis for Rn, it turns out the coordinates of it relative to this basis S is the same as it already is. And so instead of writing the coordinates of these relative to the basis S, I just wrote them as themselves because their coordinates are equal to themselves. And so in this special case, we have that the transition matrix is equal to the column built on the vectors in the old basis, only because their coordinates relative to the new basis is equal to the vectors themselves. Thus, if A is equal to this matrix is any invertible n by n matrix, then A can be viewed as the transition matrix from this basis for Rn to the standard basis for Rn. Okay, so so let's go to 4.7, which is on row space, column space, and the null space. Definition: for an m by n matrix, the vectors in Rn formed from the rows of A are called the row vectors of A. And the vectors in Rm formed from the columns of A are called the column vectors of A. Okay, so if you have an m by n matrix, the rows in that matrix are the row vectors of A. And if you look at the columns of that matrix, those are the column vectors of that matrix A. So the rows make up the row vectors, the columns make up the column vectors. Definition: if A is an m by n matrix, then the subspace of Rn spanned by the row vectors of A is called the row space of A. And the subspace of Rm spanned by the column vectors of A is called the column space of A. So what this is saying is you take all the row vectors of A, all the rows of A, and you look at the span of the rows. That's the row space of A. Also, if you take all the columns of A, one of each column, if you take the columns of A or the column vectors of A, and you look at the span of those vectors, that's the column space of matrix A. Okay. Also, another definition: the solution space of AX equals 0. The set of all vectors X that satisfy the equation AX equals 0 is called the null space of A. Okay. So the solution space of AX equals 0 is called the null space. That's a definition. So this is the definition of null space there. The definition of row space is here. And the definition of column space is here. This can be one word. Word is just use. That's correct. Okay, so next is theorem 4.7.1. A system of linear equations AX equals B is consistent if and only if B is in the column space of A. Okay, so saying that AX equals B has at least one solution or is consistent is equivalent to saying that B is in the column space of A, or that B is in the span of the columns of A. That's because if you take AX, A times X is a linear combination of the columns of A. So AX, right, is equal to a matrix A times a vector X, a column vector X, which is the solution vector of your linear system. If you look at the elements of this solution vector, x1, x2, x3, dot, 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 x sub n, that's AX. But you can think of this as, well, also, if you're looking at the matrix A, you can also think of it as built on its columns, right? So C1, let's say, is the first column of A. C2 is the second column. C3 is the third, dot, dot, dot. C sub n is the nth column. Okay, so when you take that matrix A built on its columns, the C's are the columns of A. So this is a vector itself, the entire column, first column, the entire second column, the entire third, dot, 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 entire nth. If you take A times X, this is equal to, what you're doing is you're taking X1 times C1, where C1 is a vector, plus X2 times C2, plus X3 times C3, plus dot, 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 plus Xn times Cn. Oddly, C's are now not constant. C's are the columns, and the X's are the numbers, and the values are the unknowns, but they're numbers. So what I'm doing is AX is a linear combination of the columns. And so to say that this is equal to a vector B, to say that AX equals B is consistent, is to say that there's at least one solution of this equation. Saying there's at least one solution is saying that there's at least one assignment of all the X's such that this equation holds. That's equivalent to saying that B is in the column space of A. It's equivalent to say that B is a linear combination of the columns of your matrix A. Okay, right? Being in the column space of A means that a vector can be expressed as a linear combination of the columns of A. And so because we have this equation, saying that AX equals B has at least one solution is equivalent to saying that B can be expressed as a linear combination of the columns of A, or that B is in the column space of A. Okay, so this explains theorem 4.7.1. Theorem 4.7.2. If X naught is any solution of a consistent linear system AX equals B, and if S is equal to this set is a basis for the null space of A, then every solution of AX equals B can be written as this. Okay, so X naught is any solution of AX equals B. Okay. Sorry, X equals 0. So if X naught is any solution of a consistent linear system, AX equals 0. And if S is a basis for the null space of A, then every solution of AX equals B, X can be written in this way. Wait, no, this is, sorry, so this is AX equals B. Never mind. That is AX equals B. Okay. So, okay, so then, so if you have any particular solution of AX equals B, okay, it's fine. Okay, so then, okay, so conversely, for all choices of scalars C1 to CK, the vector X in this formula is a solution of AX equals B. Okay, so once you have this equation, once you have X naught is any particular solution of X equals B, then given these vectors V here, you can plug in any numbers you want for C1 to CK, and the resultant expression here, value of that, is a solution of AX equals B. Okay, so this equation in 3 gives you all the solutions of AX equals B from one particular solution, X naught of AX equals B. So from just one solution, you have an expression for all the solutions. But it's given a basis S, vectors V1 to Vk. Okay, so you need a particular solution to X naught, and you need a basis for S, V1 to Vk. Okay. Okay, this is the general solution of AX equals 0. That linear sum, linear combination. The general solution of a consistent linear system can be expressed as the sum of a particular solution of that system and the general solution of the corresponding homogeneous system. Okay, this is the solution of this of the linear system AX equals 0. This expression. This is the solutions. All these linear combinations make up all the solutions to AX equals 0. If you add any particular solution of AX equals B, that gives you a general expression for all the solutions of AX equals B. Okay, this alone, what I'm highlighting, are all the solutions of AX equals 0. This is a particular solution of AX equals B. Adding them together gives you a general solution for all the solutions of AX equals B. Theorem 4.7.3. Elementary row operations do not change the null space of a matrix. Okay, so the null space again is the space of all the solutions to AX equals 0. If you apply elementary row operations to a matrix, then that does not change the null space of it. Theorem 4.7.4. Elementary row operations do not change the row space of a matrix. Again, the row space of a matrix is the span of the rows of a matrix. Span of the rows of a matrix. The set of all linear combinations of the rows of a matrix. That's the row space of a matrix. If you apply elementary row operations to a matrix, its row space does not change. Even though you change the matrix by elementary row operations, the span of the new rows of your new matrix is still the same, as long as you only applied elementary row operations correctly to it. Example 4. Find the basis for the null space of this matrix. Okay, so the problem is to find a basis for the null space of this given matrix. Solution. The null space of A is the solution space of AX equals 0, which has as a basis these 3 vectors. So first, I quickly tell you what the null space is. Okay, if you want, you can write the corresponding system AX equals 0, and you can find its solution space using parametric equations. I'm giving you the answer to the first part because it's just calculations we've done already. So the problem is to find this part. It's this step. but because we've done this step before, I'm glossing over this part of the problem to answer your question. So we've found solution spaces to linear spaces AX equals 0. So given this matrix A, you have a corresponding linear system represented by AX equals 0. You can find its solution space using parametric equations. And so you find it, and you can find that these three vectors span your solution space and they're linearly independent, so they form a basis. Okay, so the null space of A is the solution space of AX equals 0. You can express the set of all solutions as a linear combination of these three vectors. Because they're linearly independent and they span your solution space, they form a basis for the solution space. Okay. So when you use parametric equations to find the solution space of AX equals 0, it gives you a linear combination of vectors. If those vectors are linearly independent, then they're linearly independent and they span the solution space, and so they form a basis for the solution space. So that's what happened in example 4. Okay, I hope that answered your question. Okay, in theorem 4.7.5, if a matrix R is in row echelon form, then the row vectors with leading ones, the non-zero row vectors, form a basis for the row space of R, and the column vectors with leading ones of the row vectors form a basis for the column space of R. What does that mean? If you have a matrix R in row echelon form, there are rows that contain leading ones. Those rows alone form a basis for the row space of R. And the same leading ones, those leading ones live in columns of your matrix. If you only select the columns, and all of them, the columns that have leading ones in them, those columns form a basis for the column space of R. Okay, they're linearly independent, and their span is equal to the span of all the columns of your matrix, where the leading ones are. Okay, the rows that contain leading ones form a basis for the row space. The columns that contain leading ones form a basis for the column space. Example 6. Find the basis for the row space of this matrix. So reducing A to row echelon form, one row echelon form is that. Okay, a row echelon form of a matrix is not unique. There could be infinitely many row echelon forms of a matrix. When you get a matrix to reduced row echelon form, there's exactly one reduced row echelon form of a matrix. But getting a matrix to row echelon form is not unique. But no matter which of the possibly infinitely many row echelon forms you choose, the leading ones are always in the same place. Okay, and so even though there could be infinitely many, and probably are infinitely many row echelon forms of your matrix, all of them, all the infinitely many, always have leading ones in the exact same positions of the matrix. And so it doesn't matter which row echelon form you choose. So we have a row echelon form. Which row echelon form you choose. We have a row echelon form of this matrix A. And this is where the leading ones are, these three places. And so the row numbers are always the same. Okay, so looking at where the leading ones are, we see that the first, second, and third rows form a basis for the row space of R, right? But elementary row operations do not change the row space of a matrix by a previous theorem. A previous theorem said that elementary row operations do not change the row space of a matrix. And so, because the row space of R has as a basis the first, second, and third rows, and elementary row operations do not change the row space of a matrix, that means correspondingly the first, second, and third rows of A form a basis for the row space of A. Okay? And so that's what I wrote here, that the first, second, and third rows, denoted as R1, R2, and R3 of R, form a basis for R. Okay? So here I actually say that these three vectors also form a basis for A, and that's true. I could also ask you to find a basis using only vectors from the original matrix. In that case, you could have chosen the first, second, third rows of A, and that would also form a basis for A. But here, you can keep the same rows in this matrix and say they form a basis for the row space of your original one. Okay. Next is theorem 4.7.6. If A and B are row equivalent matrices, meaning that either matrix can be attained from the other using only elementary row operations. Then, part A, a given set of column vectors of matrix capital A is linearly independent if and only if the corresponding column vectors of A are linearly independent. Okay, so if two matrices are row equivalent, then if you take a certain set of columns in one matrix, saying they're linearly independent is equivalent to saying that the corresponding columns in the other matrix are linearly independent. So if I have a matrix A and B, and they are row equivalent, if I take the first and second columns in A and the first and second columns in B, either the first and second columns in A and the first and second columns in B are both linearly independent, or they both aren't. Okay, that's part A. Part B says a given set of column vectors of A forms a basis for the column space of A if and only if the corresponding column vectors of B form a basis for the column space of B. So this is almost like A, except it says a little bit more. It says not only does this correspondence talk about linear independence, you can say for bases. So if you have A and B as matrices are row equivalent, then if you take a certain set of columns in one and it forms a basis, then the same corresponding columns in the other also forms a basis. If a set of columns in one matrix does not form a basis for that, does not form a basis for the column space of that matrix, then correspondingly the corresponding columns in the other matrix do not form a basis for the column space of the other matrix. This is for row equivalent matrices A and B. Matrices where you can get either matrix from the other using only elementary row operations. Example 7. Find a basis for the column space of this matrix. Find a basis for the column space of this matrix that consists of column vectors of A. This is what I was talking about in the other example. In the other example, the answer was rows in the original matrix. The rows in the new matrix R form a basis for the row space of the original matrix. In this example, we want only, in this case, columns of our original matrix to form a basis for the column space of the same matrix. Solution. First, get your matrix in row echelon form. So you start with this matrix A, and you can get it to row echelon form in this way, where there are three leading ones in these positions. Okay, if you got this matrix in row echelon form, you might get a different matrix, but the ones would be in the same places. From Theorem 4.7.6 part B, if we find a set of column vectors of R that forms a basis for the column space of R, then the corresponding column vectors of A form a basis for the column space of A. So here, C1, C3, and C5 are the columns that have leading ones in them. They're all the columns that contain leading ones. They form a basis for the column space of R. Okay, so the first, third, and fifth columns, all the columns in R that have leading ones in them, form a basis for the column space of R. By our previous theorem, we know correspondingly that the first, third, and fifth columns of A form a basis for the column space of A. And so thus, the corresponding columns of A, what I just said, the first, third, and fifth columns of A form a basis for the column space of A. Because we got a collection of columns of R that form a basis for the column space of R, and A and R are row equivalent because R is the row echelon form of A. R is a matrix we got from A using only elementary row operations. And so if you get one matrix from the other using elementary row operations, that means you can get the other from the first using also elementary row operations, right? You can always go, if you go in one direction, you can go in the other one. These two matrices are row equivalent. Okay, and so we can apply the previous theorem to say that the first, third, and fifth column vectors of A form a basis for the column space of A. Okay, that's part B of this theorem right here. Theorem 4.7.6 part B. A given set of column vectors of A forms a basis for the column space of A if and only if the corresponding column vectors of B form a basis for the column space of B. Okay, we see that so we see that the first, third, and fifth column vectors form a basis for the span of the column vectors of A. Okay. Example 9. Find a basis for the row space of this matrix A, consisting entirely of row vectors from A. So we want to do something like we did in the last argument, right? But in the last argument, we're using columns. This theorem, I told you, is always about columns. Never did I mention rows. It said a given set of column vectors of A is linearly independent if and only if, then B, same thing with columns. So this entire theorem is about relating columns of one matrix with columns of the other. But we want a basis for the row space of A that talks about rows. And so this is what we do. First, you transpose A. Take the transpose of A. Switch the rows and columns of A to get the matrix called A transpose. Now that we have A transpose, get that to row echelon form. And so now the row echelon form of A transpose is one row echelon form of A transpose is this matrix. Okay? So you get A transpose. The question is about row space, basis for row space. We want a theorem that only uses columns. So switch the rows and columns of your matrix so that the rows in your original matrix A are now the columns of the matrix A transpose. So get the matrix A transpose. Now take the row echelon form of A transpose. Use the previous theorem to talk about the column space of A transpose. Find the column space of A transpose, and correspondingly, you're finding the row space of A. So you're reaching a conclusion based on the column space of A transpose, which will tell you correspondingly about the row space of A. So the row echelon form of A transpose is one of them is this, and the ones are here, here, and here. So the first, second, and fourth columns contain leading ones. So the corresponding column vectors of A transpose, the first, second, and fourth, form a basis for the column space of A transpose. Okay? They also, by our previous theorem, you mean the first, yes, so the first, second, and fourth columns of A transpose form a basis for A transpose. Correspondingly, if you now switch it back, if you switch the rows and columns back to get A, that means the first, second, and fourth rows of A form a basis for the row space of A. And that's how you do that problem. Okay? So if you want to do this problem with rows instead of columns, if you want to find basis for row space, the first step is take A transpose, apply the same procedure as the previous problem for the basis for row space, for column space, and then switch it back. Okay? So example 9 is just a very slight addition in method to this example 7. If you can do example 7, then example 9 is only taking the transpose, applying the same method of proof to find the column space, a basis for the column space of A transpose, and then correspondingly you found the basis for the row space of A. Okay, and so now that is actually the end of 4.7. And so I quickly went over all of that. Okay, so I made a video for you over the break in which I cover the rest of the material we need for the next exam. Okay, and I'm assigning this homework. Okay, so what I'm going to do now is I'm going to start talking about some of these problems now. Okay, so let's talk about some of these problems now. There's also a review in which you can ask me questions about any of these problems. And so, we have that. Okay, so let's look at homework problems. Okay, so in 4.2, numbers 3 and 9. So wait, so did I assign homework 4.2 and 4.3? I did I? Hello? Could someone just tell me? I think somebody asked me a question about it. Because I remember somebody asking me a question. Maybe it was during office hour. Okay, so I'm just going to talk about them. Okay, so in 4 points, let's just talk about them. So in 4.2, number 3, we want to determine which are subspaces of P3. Okay, so for number 3, let's talk about part A. The question is, which are subspaces of P sub 3? Okay, So, and in A says all polynomials a naught plus a1x plus a2x squared plus a3x cubed, for which a naught is equal to 0. Okay, so this is a subspace. Okay, it's closed under addition and scalar multiplication. The constant is 0 at the end. And so if you add any two polynomials with constant 0, you get another polynomial with constant 0. And if you multiply a polynomial with constant 0 by a scalar, you still have a constant 0 polynomial. So it is a subspace because it's closed under addition and scalar multiplication. Okay, so that's a little bit about that problem. Okay, for number 9, we want to talk about which are linear combinations of these matrices. So A is equal to the 2 by 2 matrix 4, 0, -2, -2. B is equal to the matrix 1, -1, 2, 3. And C is equal to the matrix that matrix. Okay, so we want to talk about which are linear combinations of those. And so in part B, there's just a very simple one. So let me do that so I can keep going with other examples. In part B, it says this matrix, right? And so this one has an obvious answer. It's 0 times A plus 0 times B plus 0 times C. That's expressing that matrix as a linear combination of those three. And so, yes, this one is a linear combination of the other three. In A and C, they give two other matrices. And so the point is to express those two other matrices as linear combinations of those three. And so that's number 9. Now in 4.3, we have numbers 4 and 11. Okay, so 4.3, we have numbers 4 and 11. And so for number 4, let's look at number 4. It says in each part, determine whether the vectors are linearly independent or linearly dependent in P sub 2. Okay, so in part A, the vectors are 2 minus x plus 4x squared. The other one is 3 plus 6x plus 2x squared. Just deleted the thing I wrote from there. 2 minus x plus 4x squared. 3 plus 6x plus 2x squared. 2 plus 10x minus 4x squared. So we want to determine whether these three vectors are linearly independent or linearly dependent in P2. Okay, so well, so if you had the set, so let me call this vector V1. Let me call this vector V2. And I'm going to call this one V3. So I'm giving them names. Okay, so the set V1, V2 is linearly independent because neither of them are scalar multiples of the other. The only way to get V2 from V1 would be to multiply this by 3/2 because 2 would have to become 3. But if I multiply -1 by 3/2, I don't get 6. V1, V2 is linearly independent as a set because neither V1 or v2 are scalar multiples of the other. Okay. And now the question is the set containing all three linearly independent or linearly dependent? So the question is, is V3 in the span of the set V1, V2? Okay. Or correspondingly, you could ask, can I express V3 as a linear combination of V1 and V2? Okay, so is there some solution to that equation? So C1 is your first constant. V1 has coordinates 2, well, it's just 2 minus x plus 4x squared, and then plus C2 times the polynomial 3 plus 6x plus 2x squared. And V3 is vector 2 plus 10x minus 4x squared. Okay, and so that means that the constant is 2 equals 2c1 plus 3c2. The other term is 10x. 10x is equal to negative c1x plus 6c2x. So that means you have, so you have that. Then you have negative 4x squared is equal to 4c1x squared plus 2c2x squared. Okay, so we have these three equations, okay, which correspondingly tells you that you have this first equation. You have the second one, but the x's, you don't really need them. You have 10 is equal to negative c1 plus 6c2. And then the third equation, you have this. But here you have negative 4 has to equal 4c1 plus 2c2. So what you want are c1 and c2 that satisfy all three of these equations. Okay, so are there values of c1, c2 that satisfy all three equations? Okay, and so correspondingly, you have three equations, two unknowns. Okay, so you have So you have 2, 3, negative 1, 6, 4, 2. Then here you have 2, 10, negative 4. And you get this to reducer echelon form. And the result, this again, and then copy. Okay, so now multiply this by half. Add this to this, so you get 0, 15 halves, 11, negative 4 times the first row to the third, you get 0, negative 4, negative 8. 15 halves is 7.5. I'm going to write 7.5 so that, okay, still doesn't mind. This is 1.5. There we go. Okay, so now I want to get this to row echelon form at least. So this is going to be 1, 1.5, 1, 0. Now I'm going to multiply this by 1 over 7.5 or 2/15. This is 22 over 15. And then I'm going to 4 times this row to the other one and get 0, 0, 88 over 15 minus 8. 32 over 15. Wait, no. 88 over 15 minus 32. Okay, so then negative 32 over 15. And okay, so now you get this. So the problem here is that you have zeros here and you have a negative number here. So this system is inconsistent. Okay, you just find the solutions of this system and you find it's inconsistent because you have a row of zeros here equals to this. So this system is inconsistent. And so that means that V3 cannot be expressed as a linear combination of V1 and V2. Oh, so that's good. Okay, so then well, so V3 is not in the span of V1 and V2, and so you can add it. So you can add it to the set V1, V2, which is already linearly independent, and still have a linearly independent set. Okay, and so the conclusion is that the set of three things is linearly independent. These three vectors are linearly independent of P2. Conclusion is that they are linearly independent in P3. Okay, and so that is explaining that problem. Okay, in 4.3. Now, in 4.4, we have numbers 9 and 11. 9 and 14. Okay, so let's look at that. So 4.4, you have numbers 9 and 14. So let's do number 14. Okay, so 14 says find the coordinate vector of P relative to the basis S, which is equal to the set P1, P2, P3 for piece 2. Okay, and so let's look at A, which has the vector P, little lowercase p, which is equal to 4 minus 3x plus x squared. P1, which is equal to 1. P2, which is equal to x. And P3, which is equal to x squared. Okay, so we want to find the coordinate vector of P relative to that basis. So P here, which is equal to this, is equal to that, is equal to 4 times 1 minus 3 times x plus 1 times x squared. And I put the parentheses there to point something out. The 1 is P1, so that's 4P1 minus 3 times x, which is P2, plus 1 times x squared, which is P3. I've now written P as a linear combination of P1, P2, and P3, which are the basis vectors in basis S. So that means that the coordinates of that vector V relative to this basis S is equal to 4, negative 3, 1. That's the coordinates of V relative to that basis S. So that's part A of 14. Okay, so that's another problem. Now let's look at 4.5, number 6 and 15. So for 4.5, numbers 6 and 15. Okay, so 4.5, numbers 6 and 15. Okay, so for number 4.5, number 6 and 15. So for number 15, it says the vectors v1 is equal to 1 comma negative 2 comma 3, and v2 is equal to the vector 0 comma 5 comma negative 3 are linearly independent, right? Because neither is a scalar multiple of the other, and it's 2 elements in the set. Enlarge v1 comma v2 to a basis for R3. Okay, and so we want to enlarge that set v1, v2 to a basis for R3. So we just need a vector that's not in the span of v1 and v2. Okay, so let's find a vector that's not in the span of v1, v2. So let's do v1. Let's take the cross product of v1 and v2, because the cross product is a vector that's perpendicular to both v1 and v2. And so since it's in the it's in the vector space perpendicular to the plane through those two vectors, it's linearly independent with both v1. v1 cross v2 is perpendicular to both v1 and v2, and it's linearly dependent. So you find v1 cross v2, and so you do that ijk in the first column. v1 is in this column, 1, negative 2, 3, and then this is 0, 5, negative 3, and so you find the determinant of that, and this is I times, and then you get 6 minus 15, which is negative 9, then minus j times the determinant of the corresponding submatrix there, and you get negative 3. This is plus k times the determinant of the corresponding submatrix, which is 5. And so this is equal to negative 9i plus 3j plus 5k. And so this is equal to the vector negative 9, comma 3, comma 5. And so this vector is the cross product of v1 and v2. And so negative 9, comma 3, comma 5 is not in the span of the set v1, is not in the span of the set v1, comma v2. And so since it's not in the span of those two, is not in the span of it, you can add it to the set and it's still linearly independent. Thus, by the plus minus theorem, the set v1, v2, v3 is linearly independent. Okay? And so just take cross product two vectors, the result is not in the span of the two vectors. And so because it's not in the plane through those two vectors, so it's not in the span. And so that new set is also linearly independent. So I enlarged it. So that's linearly independent as a set with exactly 3 vectors. It forms a basis for R3. That's because R3 is 3-dimensional and the set has 3 things in it. So we only need to show it's linearly independent or spans R3. So since we know it's linearly independent, and it's the same number of vectors as the dimension of the space it's in, it's enough to show in that special case that it forms a basis for R3. So now the example is done. So that's an example from 4.5. Now for 4.6, we have 3 and 6. Okay, so for 4.6, we have 3 and 6. Okay, so this is homework for next class. I'll let you do that. It also takes some time to think about them. So I want to see, can I do something quickly? So 4.7 is 15 and 17. Okay. Okay, so the other one require more time. So for homework, you have all this homework to do. Okay. To help you out, I started doing a lot of it. Okay, so these are solutions to a lot of the problems already. Okay, so I want you to work on the other ones, and I want you to watch the video on YouTube. Okay, so on YouTube, I posted a video. It's already posted on YouTube. I'll just put it on the playlist for you, and so it'll be easier to see when I put on the playlist, but it's already there. So your homework is to do those homework problems that I listed here, which is a lot of them, and to watch the video and continue doing homework for these 3 sections. Okay, so you have a week to do these homework problems. The lesson goes into chapter 5, but there's no homework on chapter 5 right now because you're only worried about test 2. Okay, so when we meet next class, this lesson and the next lesson that you watch will cover all the material for second exam, and we'll have a review class next class where I can go over homework or anything you want. Okay, so you have over a week to study, and the video is already up. If you watch it tomorrow, you have over a week having all the material ready. Okay, so here's the homework. This is everything you need to know. These are the announcements. And so have a good Thanksgiving, and I will see you in a week on Tuesday. Okay? Happy Thanksgiving. Have a good night. Have a wonderful Thanksgiving. See you next week. Take care. Bye. I'm going to save the whiteboard, post that also. Okay. Good. Sure. You know what? I will post the lesson notes also. Okay, so on Blackboard there'll also be the lesson notes. The video's on there, and I can post the lesson notes also. Okay, so I'll post both of it on Blackboard and on YouTube. You can watch the video also. Okay, it'll be just like this lesson. Okay, have a nice weekend.